So, is light a wave or a particle? Well, we've got good evidence to suggest that it's a wave. It does a lot of the same things that a water wave does. It reflects, that's why you can see the phone right now. It diffracts, it spreads out as it passes through a small gap. That's why you can see an interference pattern spread out. And it also refracts, right? That's why you can see this transparent rod, because the light is bending as it passes through it, and you see the distortion. But is that the whole story? Well, to answer that question, we need to think about what ionization is. Ionization is the addition or removal of an electron from an atom. If you imagine this tower of cups here is a collection of electrons that are bound to an atom. When they absorb enough energy from, say, a high-energy gamma wave, one of them will be emitted. But why? Surely it shouldn't matter. If light is just a wave, then even a radio wave should be able to emit an electron. It might take just a bit longer for the radio wave to emit the electron, whereas it would take quite a short time for a gamma wave. But if it's a wave continually giving its energy to that electron, it should get emitted at some point. Just like water waves continuously erode the shoreline, you don't need to wait for a tsunami or a storm for that to happen. So the question is, does that happen? Can radio waves cause ionization? Is light just a wave? And the answer? No. So there must be something else going on. And that is that light is also a particle called a photon. You can get low energy, low frequency photons, like radio photons. And these ones individually do not have enough energy to emit that electron. In fact, you could have a whole cup load of them and you're not going to get an electron being emitted. So what do you need to do? You need to have a higher energy photon, like a gamma photon or an X-ray photon. In that case, we just pretend that didn't happen. In that case, you can get one electron being knocked off that atom. If I was to throw more photons, at this group of electrons, again, just pretend only two went off, you would get more electrons being emitted. Okay? So once you've reached that minimum energy to remove the electron from the atom, and that's called the work function, once you've reached that, the more photons that you throw at your electrons, the more electrons are going to be emitted. But if you don't reach that limit, it doesn't matter how many you throw, you're not going to get any electrons emitted. In fact, Einstein put it quite nicely in a quote where he said that the simplest conception is that a light quantum transfers its entire energy to a single electron. And what that was a perfect German accent. So you're welcome. If we look at the energy diagram of what's going on, what we've got here is the green bit is like the atom, or the material. The blue bit down here, well, that's your electron, bound to the atom. And this line here indicates the minimum energy you need to get that electron emitted from that atom. That's called the work function, E0. So if you imagine that a photon comes in with an energy less than the work function, well, the electron's going to say, sort of, not worth getting out of bed for. So it's going to stay bounded to the material. It might move up an energy level or two, but it's not going to be removed from that atom. Okay, scenario number two. The photon comes in, and that just has exactly the right amount of energy to remove the electron from the atom. It's the same energy as the work function. in which case the photon gets removed from the material. Okay? So it feels like, okay, fine, I'll get out of bed, but you know, I'm not leaving my room. But fine, you've got me out of bed. Third example is, let's say the photon has energy that is even more than the work function. What happens there? Well, in that case, the electron will be emitted, but where does that extra energy go? Well, it turns into kinetic energy. If you imagine that you were this electron, it would be like someone telling you that you had physics that day. Yeah? So you would certainly get out of your bed, but then you would go and run to school. Just run. And that would be your extra kinetic energy. That's pretty much exactly what's going on here. So, as an equation, the energy of the photon that came in is a combination of the work function, the minimum energy needed to release the electron, plus the kinetic energy of the electron. And you can also write this as hf, so that's the frequency of the photon that came in, times Planck's constant, equals the threshold frequency, right, the minimum frequency you need to emit the electron, plus a half mv squared for kinetic energy. So, whether you think that light behaves as a wave or a particle, you're correct. If you think it behaves as neither, then either you're a revolutionary genius, or you need to watch this video again. I'll leave that up to you.